Bismillahirrahmanirrahim, dear students. Assalamu alaikum. Welcome to the Electrical Engineering channel. In this lecture, I will discuss some numerical problems on electrodynamics, magnetic fields, curl, electric current density, and similar terms. So, this is the first and the simplest example. And in with this example, we have to determine the value of magnetic field intensity for a current of 15 amperes flowing in the AZ direction. So H is to be found out at this point, and we know that H is equal to I over 2 pi rho A phi for an infinitely long current carrying conductor or filament, and we can substitute the values of all the terms in this expression. And here rho will be equal to square root of x square plus y square, and y is equal to 0, so rho will be equal to square root of x square, so that will be equal to 20 under root I is equal to 15 amperes, and the unit vector is a phi. So this is equal to 0.534 a phi, and we have to determine the magnetic field intensity in Cartesian components, so we can convert it to hx and hy components, and hx is equal to h dot ax, so that will be equal to this term into a phi dot ax, which is equal to sine phi, and phi is equal to tangent inverse y over x, and it is equal to 0, so h x will be equal to 0. Similarly, hy will be equal to this term into a phi dot ay, and it is equal to 0.534 cos of phi, right? A phi dot ay is equal to cos phi, so it will be cos 0, and hy is equal to 0.534, so h will be equal to 0.534 ay amperes per meter. So let's solve another example, and in this example we have to determine the magnetic field intensity at this point in a coaxial cable, and the coaxial cable has these dimensions. The inner conductor has the radius of 0.3 meters, and the outer conductor has inner radius of 0.5 and outer radius of 0.6, and the current which is flowing in the inner conductor is equal to 2.5 amperes along AZ. So let's first evaluate rho, and rho is equal to x square plus y square under root, and it will be equal to 0.2, and this is actually rho which is 0.2, and we can observe that this rho is less than a. So for the region when rho is less than a, the magnetic field intensity is equal to I rho over 2 pi a square a phi, and this is the same expression that we derived while we were discussing the application of Ampere's law for coaxial cable. So we know rho, we know all other quantities, and phi is equal to tangent inverse y over x, and it will be equal to tangent inverse infinity, and it will be equal to pi by 2 or 90 degrees. So that is equal to 0.8842 a phi. So this is h. Now convert this h to Cartesian components, and hx is equal to h dot ax, and that will be equal to 0.8842 minus sine phi, right? And hx will be equal to this term. Similarly, hy is equal to h dot ay, and it will be equal to cos phi, so cos 90 will be equal to 0, so h will be equal to 0.8842 ax. Okay, so let's solve another example, and in this example we are given three sheets which are carrying surface currents of k1 equal to 2.7 ax at this location, k2 is equal to minus 1.4 ax at this location, this is the second location, 0.15, and k3 is equal to minus 1.3 ax at y is equal to 0.25. So this is this sheet which is carrying a current, and all these sheets are carrying current in the ax direction, and we have to find out magnetic field at p0 0.20. So h is equal to 1 by 2 k cross an, and we have to remember the expression for electric field due to surface charge. So for an infinite sheet of charge, E was equal to rho s over 2 epsilon an. So the similar expression in magnetic field is H is equal to 1 by 2. This is surface current density instead of surface charge density, and cross product with an. And there is no term which is characterizing the medium because the magnetic field intensity is independent of the medium, and K is the surface current density in ampere per meters. So H1 is equal to 1 by 2 K1 cross AN, K1 cross AN, and it will be equal to 1 by 2, 2.7, and AX cross AY. So here AN is equal to AY, and that will be equal to 1.35 AZ. Similarly, H2 will be equal to 1 by 2 K2 cross AN, and it is equal to AX dot AY minus 0.7 AZ. Similarly, H3 will be equal to 1 by 2 K3 cross AN, and it is equal to 1 by 2 minus 1.3 AX cross minus AY. So this K2 is actually minus 1.4 AX. So it is actually minus 1.4. So I have missed minus sign over here. So if we put a minus sign over here, the answer will be equal to minus 0.7 AZ. So answer is correct, but I have missed negative sign from this term. And the third magnetic field intensity is equal to this expression, and 1 by 2 minus 1.3, because again this is the opposite current along the minus AX direction, and AX cross minus AY. So that will be equal to minus AZ, and minus minus will be plus, so it will be 0.65 AZ. So why do we have a negative sign with this AY over here? The reason is that the point at which we want to measure magnetic field lies somewhere over here between this sheet and this sheet. So AN with refer to this sheet will be AY. With refer to this sheet, again AN will be equal to AY, but with reference to this sheet, AN will be equal to minus AY, because it is lying in the opposite direction on the left side of this sheet. So that's why we have put a minus AY over here, and H will be equal to the sum of all these three magnetic fields, and it is equal to 1.3 AZ ampere per meters. So another example can be solved, and in this example we have to determine the curl of H, and H is equal to x square z AY minus y square x AZ, and let's evaluate volume current density J at this point. So J is equal to del cross H, so let's evaluate del cross H, and that will be equal to this determinant, and it will be equal to partial over partial y of minus y square x minus partial over partial z x square z ax, minus ay partial over partial x minus y square x plus az into partial over partial x x square z. So let's evaluate these derivatives, partial derivatives, and at the end we get this expression, and we will put the coordinates of this point, and final value of volume current density J is equal to this expression. So this is in ampere per meter square. Okay, so that is all about our today's lecture, and I hope you have understood the concepts which are discussed in this video. For watching more videos, please subscribe this channel. Until the next lecture, it's goodbye.